Well, Michelle, thank you very much for helping organize and get this running. I'm Keith Gray. I am the Director of High Performance Computing at BP for a bit more. And thanks everyone for joining this session. I hope we will have a good conversation, as well as I know we're going to have some great presentations. So let's go ahead and get into the session right now. To start it off, I wanted to just throw a little bit of a challenge into the room with an assertion that the next 5 years are likely to see substantial changes in how we are architecting, delivering high-performance computing clusters in support of the energy industry, that the computing industry is changing dramatically, but our industry is likely to go through incredible change. And for us to deliver that successfully, we're going to have to be really thoughtful. We're going to have to do a lot of planning, and we're going to have to anticipate the changes, because I don't think there'll be anything that is a step change. It's just going to take lots of energy to take advantage and leverage all the evolutionary changes. And I do think that when we look back, that if we're able to successfully retain and then train the talented people that will be required to accomplish this, if we're able to think, anticipate, plan, and leverage the changes that are going on in the broader HPC market, then we can be a really key contributor to the change in energy. My assertion is that the application mix that we're challenged to support will change pretty dramatically. I do believe seismic imaging requirements are going to continue to grow and continue to dominate high-performance computing and energy. We need to deliver higher resolution. We have researchers that are developing tools that use the full elastic wave propagation. The algorithms are getting more complex, but the people involved in seismic are going to be challenged to deal with even bigger data sets with fewer experts. So we're going to likely see technologies that need to look through the data using the computer, that make a first draft at an interpretation, and do more to let us iterate through our data volumes even more quickly. But to accomplish that and to support the coming requirements, machine learning is going to be a more important part of the application mix, and it's going to require additional skills. One of the key topics for today will be discussing containers. We do believe that containers are going to be important as we bring in additional applications into HPC. My first bad joke and sarcasm of the morning is that we're likely to see new versions of these ML applications arrive about every 30 minutes. We know that we're going to have additional projects coming in and additional technologies that we need to support, from carbon capture, use, and sequestration, where we need even higher resolution reservoir simulations to ensure that the reservoirs that we are inserting carbon will be able to hold those for generations. We know that we'll have additional growth in fields like wind energy, where to optimize the fields to ensure that our companies can be cost effective and profitable, we're going to have to leverage the skills in computational science that we've got to create a competitive advantage. We know that molecular modeling, looking at ways of improving combustion and understanding the rock structures, understanding the chemical structures of catalysts, leveraging computational fluid dynamics for the work that we're doing is going to require us to be able to deliver these capabilities for our companies. But that does create additional complexity in how we evaluate technologies, how we plan for future acquisitions, and how do we optimize the investments we're making in high-performance computing systems to make sure that all of the different applications can work effectively in the systems. The most expensive computer that we can acquire is the one that sits idle. So we've got to find ways of ensuring that we can use the system effectively. Even as oil and gas exploration is challenged to be more effective, we know that one of the key ways is to deliver higher resolution. We're going to have higher density node surveys, both on land and marine. We're coming up with ways to acquire streamer surveys more effectively. The data volumes that we're going to face continue to grow. But the processors that we'll have to choose from will get more diverse. Over the last 10 years, the decisions have been relatively simple. We've had one vendor that dominated the server market. But as we've looked over the last few years, price performance improvements have been a bit more challenging to deliver. Some experiments like KNL were at point solutions quite effective for some companies, but have not been adopted more broadly in the marketplace. We've got to look at how systems like that will come in, be valuable. GPU systems have been a great fit for some workloads, but probably not for all. The exascale systems are coming forward, and we know that they're demonstrating the coming diversity. The Fugaku system in Japan is based on an ARM processor with high bandwidth memory. The Frontier system at Oak Ridge is using AMD processors and GPUs. The A21 system is using Intel procs and GPUs. The Perlmutter system at NERSC is using AMD CPUs and NVIDIA GPUs. That's going to create, with this level of diversity, we're going to have to get better at evaluating new technologies. We're going to have to find the right benchmarks to run. We're likely to have to automate some of those benchmarks so that we can do this as fast as new technologies are coming at us. Storage and memory hierarchies are evolving. High bandwidth memory can deliver a key step change for memory-bound applications, and those define a lot of the workloads that we've had to deal with in oil and gas. And we know that they'll be quite key as we go forward into an evolving energy industry. Non-volatile memory is a unique opportunity, but how's it going to fit for our workloads? Flash pricing continues to fall. It's putting more challenge on vendors that deliver hard drives. Many industries are looking at hard drives solely as archive, but we still need them for our principal file systems. And our industry is still quite committed to tape. We use tape to move data from the field to the HPC facilities. We use tape to archive huge data volumes. And we have warehouses full of old tape that we still have to deal with. We know that the density and the thermal loads created by future procs is going to continue to grow. Today, a typical proc can be in the range of 150 to 200 watts. We see roadmaps that have that growing by a factor of 3 to 4. We've already been challenged to cool systems with air. The highest air-cooled systems that BP has delivered are in the range of 30 to 32 kW per rack. But with higher density procs, with more dense computers, we know that direct liquid cooling and immersive cooling will continue to be important. But to deliver that is going to take really effective communication between the HPC teams and the facilities teams. It's going to take a lot of planning and a lot of advanced work to make sure that we're telling the facilities people early enough so they can make the necessary changes. The cloud is a business model for delivering HPC. We're going to have to be recognized by our corporate leaders that we're honest brokers about the cloud. We're going to have to be ready to leverage it when it makes good business sense. We're going to have to be considered trustworthy and reliable when we're talking to our leadership about when the cloud fits and when it doesn't. We're going to have to put together real credible evaluations and explain why it makes sense. We're going to have open and good conversations with the cloud vendors so they understand our requirements. And if we do want to use the cloud, we're going to have to explain and do thoughtful testing and challenge them to deliver systems that meet our needs. As we see more people coming to the HPC beyond the traditional lunatic fringe of seismic imagers and reservoir simulations guys that we supported in the past, we're going to have people coming in who don't have the depth and experience in using command line. So we're going to have to develop better workflow tools. We're going to expect that the researchers coming in and the new people coming in will want to use tools like Python that allow them to be more productive more quickly. The hardware architectures will have different programming models. So we're going to have to find ways to abstract that away from the people who are trying to create new ideas. And then when their ideas are ready to be deployed more widely, our teams are going to need the skills to optimize and ensure they run effectively. To actually pull that off, we're going to need to make sure that the systems teams are deeply connected with the software developers and the researchers. We're going to have to act like we're one team. Keeping the skills and the dedicated, hardworking systems teams together is going to be an interesting challenge. People don't come out of university with the skills to step into a systems role immediately. We're going to have to make investments in their training. We're going to have to collaborate as an industry, and we're going to have to leverage the efforts of leaders like TACC to put together both the technical training as well as the business training to help people understand how to deal with more complex systems, how to understand the changes that are coming, and how to instrument and manage and deliver reliable HPC systems. Let me stop there and turn it over to Tommy Minyard to lead a conversation on how TACC is delivering machine learning and analytics capabilities through containers. Tommy, you ready to go?
Yep, thanks, Keith. Well, I'm going to get my screen shared here. Sorry, my screen just freaked out. There we go. All right. Y'all seeing the right one?
I think you just went to the presenter view.
Okay. Thanks, everybody. Thanks, Keith. That was a fantastic lead in to my topic of discussion today, which is going to be HPC containers and our experiences at Singularity and Charliecloud. I did want to set the stage a little bit, though, on containers and back up a little bit and talk about why containers could be such a huge impact for HPC. Basically, the whole concept is that with a container, you can encapsulate and package up all of your application binaries, libraries, dependencies, and everything that you need to execute a process or a task. And it really encapsulates the full software ecosystem where you're working, except for the kernel and the lower level OS libraries that are running on a typical system. I do want to emphasize this is not the same as a virtual machine. Those of you in HPC that may have tried virtual machines know the performance impact that the virtual machine can have. And those system administrators, I like to allude that this is more like a change root environment. In fact, it's change root on steroids, basically. So it is dependent on a host OS. So you do need to have typically Linux installed on a system before you can run one of these containers on it. And it uses namespaces so that it can isolate what's going on the system level from what's going on in the container. So most of you may have heard of Docker. Docker was the leading container runtime. It's been used extensively in the cloud and enterprise, and you know, this has been a foundation for much of Kubernetes and Google Cloud. It's supported on the Amazon cloud. It's been used extensively out there in enterprise and industry for DevOps, for quickly rapid deployment. It's kind of the 6 key items that are pillars of the containers. Number one, it's portability. You want to have the same software version available on multiple different platforms. Usability. I mean, it's easy to use. You know your environment. You can just deploy your container. You can make it usable on whatever system you might be using it on. Accessibility, again, you have access to whatever tools you want in your container environment, and you can build in whatever you might want to do, which leads into the packageability. You can package it all together. You can deploy it. You can give it to other folks that may want to reproduce what some of your work has done. And of course, you have full control over what software choices and versions are tied As Keith already joked, we are seeing new machine learning codes about every 30 minutes, and it's challenging, extremely challenging from an HPC point of view with our environments to keep up with these evolving software technologies. I do want to emphasize all workload software can actually be distributed as a container. You can containerize pretty much any of your software workloads or processes and distribute it like that. And so it's a concept that in HPC we're going to have to adopt. I do want to give credit to Andrew Young from Sandia National Labs. He presented a lot of this at SOS 24 last week and had a lot of good information that I lifted from this talk. So what we want to think about now is, well, can HPC leverage containers? One of the big aspects on containers is, sorry, let me start my video, is the fact that they're very popular, so you can allow flexible deployment and development in a containerized environments. HPC, unfortunately, is not typically as flexible. In our environments, we've got a large number of resources that are shared between many users and groups. Very static software environments. I know at TACC, we're very careful about changing software environments and deploying updates and tools to make sure that we don't break something or make a change that impacts performance or even running of the applications in the environments. And really our environments, this is one of the struggles we have. We don't support all these emerging apps and workflows. It's, somebody needs a newest version of Python to be able to build something. Well, it's going to take us a while before we're going to deploy that version potentially. And it's really hard for us to keep up. We're still primarily running CentOS and RHEL 7 environments just because we haven't had the time and comfort level to get RHEL 8 and CentOS 8 up and running on a lot of environments. So, but if we can support these containers in the HPC environment, we could address a lot of these inflexibilities and limitations that we have on our HPC environments. But can we make sure that when we adapt these programming environments into containers, that we still get performance and security on our HPC systems? Obviously, we don't want users getting root, which is definitely a no-no on our systems. So if we think about that and look about the cloud, what the cloud offers, okay? Well, our big challenge from an HPC point of view right now is cloud is dominating the vendor hardware choices, and the software in the cloud is just constantly rapidly evolving and changing, and just keeping up is next to impossible. And of course, some new HPC workloads and processes such as AI, machine learning, are being developed in these cloud environments, and then they expect us to be able to deploy it, and we just can't. I can't run the latest TensorFlow. I don't have the right software builds on my HPC system. And really, what the cloud allows is adaptable models and usage models. They have a surface model based, but you can deploy your own resources on those services. They have guarantees and failover migration. They let you deploy whatever software you want in your images. That's something we can't do on an HPC system effectively. However, we've done the cost analysis and looked, what if we went and tried to run our entire HPC environment in the cloud? And as Keith already alluded to, there's many challenges to support HPC in the cloud: networks, storage. But even if you just looked at the cost of buying equivalent cloud time in the cloud, it's still way more than what it costs us to do on-prem in terms of deploying HPC systems. And that doesn't even include the cost of data storage or even network transfer in the cloud environment. So, however, we should learn from what the cloud is doing in these DevOps and these rapidly evolving software environments, leverage what we can, but we still got to make sure we focus on maximum performance for our applications. We buy these very expensive processors. We want to make sure every cycle is going to the application, not to the software layers, to be able to manage and run in your environments. So, all right. Now, there's really contradictory requirements when we talk about HPC environments and cloud environments. HPC, we use batch scheduling. We use cluster provisioning software deployments, very static software deployed on each of the compute nodes. They all look identical. We absolutely require low latency high bandwidth networks. We run tightly coupled applications at large scale. And you know, the Ethernet networks don't quite fit the bill. Typically, we need something that's a little bit lower latency and can deliver more consistent performance. And of course, we have limited resources, so there's usually some kind of batch queue. You know, users have to submit job, wait in line. This batch queue scheduler tries to do the best in terms of making sure that the nodes are all utilized and that the compute environment is running like expected. Cloud environments are completely different. You have flexible cloud infrastructure with service orchestration. You can do constant deployment, integration of new software, keep rolling it out, do DevOps. You have almost unlimited resources. If you can afford it, you can spin up new instances pretty much on demand. And you know, that's just not something that we have in the HPC environment. So, but you know, containers and the containers I'm going to talk about today do help us bridge some of these requirements, and so we can make HPC systems kind of look more like a cloud environment. And I have to admit, I was very skeptical of cloud and containers early on, but seeing the power and the ability to support communities that we haven't typically supported here at TACC, especially computational biologists. They are big adopters of containers, and now we can support a much bigger community than we've ever had to deal with before. So let's switch a little bit and talk about some of the containers and the tools out there. I mentioned Docker previously, but from the point of view of HPC, Docker and HPC do not mix. It's definitely been the most popular and is still the most widely probably used container runtime build environment. But really the problem with Docker is once you have it running on a system and users have access to it, you pretty much give them root level access to the system where it's running. And I'm sure most of you other system administrators and CTOs out there, you definitely don't want users to have a root on your system. I definitely don't want that. And so that's an absolute no for HPC shared resources. And unfortunately, with the way Docker is currently designed, it just can't be fixed in the current Docker runtime itself. The way it's built and designed with this client daemon architecture, they just can't fix it in the current configuration. This climate daemon architecture is great for cloud services world, but bad for HPC. You know, we spend a lot of time on our compute nodes making sure that we don't have daemons that are spinning up and potentially impacting performance. And we try to run very lightweight kernels and processes on all the compute nodes just to make sure that all the performance and CPU cycles are going to the application. So, the thing is you can use Docker on your laptop and workstation, but that does assume you actually have root access and have machine control or authorization to have root. This has probably been the biggest limitation for Docker adoption on HPC environments. The main problem we have right now is if a user comes to us and say, hey, I want to build an image, I can't give them an environment or a location like a login node where they can go build an image. They have to find another system where they have root privilege, whether it's their own desktop workstation, and then they can build the image there. But then that introduces some other potential challenges that I'll discuss on an upcoming slide here in a few minutes. So, but anyway, in terms of Docker, you know, it's very flexible. It just works. I do have it deployed in some environments where we feel it's good for prototyping and testing stuff, but it's not on HPC systems right now. So now let's talk about some of the HPC container runtimes. So because Docker has these limitations, many sites, including DOE and other researchers, figured out, hey, we can maybe take some of these Docker concepts and everything, address some of the issues like not giving them root privilege, and maybe allow HPC sites to deploy these containers in their environments. The first and most popular that I'm aware of was Singularity. Greg Kurtzer was one of the developers there, and I remember he hit me up at Supercomputing early on, and I was skeptical initially, but you know, I kind of swung and seen a little bit of the benefits of containers right now. So Charliecloud is another one, also developed at a DOE lab. Shifter was originally designed for a Cray, done by Norsk and Shane Cannon out there, but he's adopted that now for Linux as well. And there's Soares. I'm not as familiar with Soares, but I have heard that it's kind of flexible, similar to Charliecloud type of environment. So, but what's important is these runtimes, are slightly different in terms of their designs and the way they handle OS mechanisms. They have slightly different storage and management of images. They deal a little bit differently in how they handle user PID and mount namespaces. Some of it have slightly different models in terms of deployment and security. Some are, completely user-based. Some do require some administrator privilege to install. They also, have different image signing, validation registries available to them, but all of them support conversion of Docker images. And this is kind of the more important thing, is it allows people to build Docker images and deploy them into these container environments. Now, the good news is there's rootless container build tools under development. I'll a slide on that a little bit later. For now, this is kind of the mechanisms we have to have to be able to build and operate these container runtimes. Hold on. Sorry, just got a chat there. All right, so let's talk about HPC container performance. And this is really one of the key aspects of something we have to address and focus on for HPC. We don't want to lose any performance of our applications by running them in container environments. And of course, if you use virtual machines, they do suffer performance ability when accessing hardware, just because of the nature of the way they operate. But we have seen multiple papers. In fact, here at TACC, we've done some studies, and I'll present some results later, where we show that there's actually minimal loss in performance when using containers. Andrew Young and his colleague Bedretti posted this about the first petascale ARM system last year. Before that, there was another HPC runtime, paper presented at the Canopy conference in 2019. But there are some additional overhead when you talk about containers. There's some startup overhead. You have to be able to initialize and bring up the container. Another thing that you kind of need to take consideration in HPC environments is the container image does have some size to it. If you have it on a shared file system, like a Lustre file system, or unfortunately, if it's NFS, it's going to put some pretty severe stress if you launch that image, like an MPI job from many computes at the same time.
Hey, Tommy.
Yes, go ahead.
I don't think you're sharing your slides.
Oh, did they stop sharing? Sorry, somebody took over. Hold on. Sorry. I think somebody took over the share screen. Sorry about that. All right. All right, so I was mentioning that you can see him now.
Yeah.
Okay. So well, as I was mentioning, when you do launch your container on many nodes at the same time, if it's reading from a file system, it's going to put some stress on it. The downside is, of course, we can't really install images on all the compute nodes, because then that defeats the purpose of being able to allow people to rapidly change them, and we couldn't just constantly be deploying new images on all the compute nodes. So this is one of the things we're still trying to get a handle on, and how we might be able to better support this. All right, so let's talk a little bit about the container challenges on HPC systems. One of the bigger ones that we struggle with is not all MPI libraries are supported by containers, and it's kind of a criteria that we really need to have for supporting all the applications we want to run on HPC systems. When users deploy and operate their container, they need to use a matching MPI, or at least something compatible for the hosted PMI configurations. OpenMPI and MPICH don't always agree with each other and are implementation dependent. There are some workarounds and some hacks you can make with LD preload to make things work. It makes the container a little bit portable, but it's not easily reproducible at lots of sites. And again, I mentioned it was implementation dependent in terms of InPitch or OpenMPI. And there are some glibc compatibility issues, so you do need to be a little bit careful with that with MPI. The other challenge is, of course, the build machine for the container may not actually match what you have on your HPC compute nodes. I mentioned, before, users have to build on their desktop or workstation to be able to build their images, and it may not have the same processor that's on the system. So if you have a ARM or Power 9, you're going to need to have build nodes for that architecture that users can do their container builds on. Even if you're supporting x86 and your laptop has x86, it may not actually use the right instructions to leverage best performance on the various chip processors that are in the HPC systems. In a lot of cases, when you make when you build a library, it makes assumptions of build time for what optimizations for the processor, and they may not be performant on the actual system you go to run on. And of course, if you choose instructions that are not supported on the system you run on, well, then you're just going to get seg faults and your application is just going to crash every time. The other big challenge in terms of HPC systems, we need to be able to launch these containers under batch environments and handle a lot of the scheduler launch mechanisms, whether it be Slurm, PBS, whatever scheduler you might be using on your system. And right now there's no integration and no knowledge about the scheduler goes to launch a container or anything. We feel that there could be some more tightly coupling between that information and help be able to be more efficient whenever you're running containers under the batch environments. There's really no standardization of HPC container runtimes right now. And of course, running on the HPC environments is completely different from the way users typically operate in the cloud. And I like to call it performance, portability, conundrum. The challenge here is you can make a really portable container, but it's probably not going to be the best performance. And of course, if you make the best performing container on your HPC system, well, it's probably not going to be portable to every platform. And so there's kind of this middle ground and a continuum between performance and portability that you kind of have to walk, depending on what type of application or container you're building. So, all right. So now I want to switch gears a little bit and focus on Singularity and Charliecloud. So those are the two that we've had the most experience with at TACC, and it's two pretty flexible ones that have slightly different ways that they are handled, but do support the container environment. So first is, of course, as I mentioned, Singularity. It was the first one we really supported at TACC. We deployed it on Stampede 2 and currently have it on Frontera. But we handle this through RPMs. So basically, our HPC team builds an RPM that contains all the Singularity pieces in it, and then hands it over to the systems team to deploy on each of the production systems. Unfortunately, Singularity does require system administrator installation. From our point of view, what we do is we take the Singularity RPM, and we install it on all the compute nodes. Installed with that RPM includes the configuration files and everything needed and modules and everything needed to load the environment to be able to access Singularity. So one trick we do though is we install a dummy module and a script on the login, so that if anybody tries to actually run Singularity on the login nodes, it says, hey, you need to actually submit and run this through Slurm on the compute nodes and not on the logins. So we don't have a full Singularity install on the logins. And again, it's mainly because I don't want people spinning up Singularity images and apps on the login nodes. That I want them to be able to run only on the compute nodes. Otherwise, I just have dozens of Singularity images running on the logins. So it was pretty trivial to build and install the Singularity. We made a couple of minor modifications to the configuration file that's installed with the RPM. We made sure to add our Lustre and local file system bind point path This means that they'll be able to put those file systems and paths into the image. And we also disable overlay and set to no. The default option is to try, and we don't want users trying to do any overlay in the images as of yet. I'd have to ask the HPC guys why they decided to disable that, but I went with their recommendation on that. In terms of usage, the biggest usage we have for Singularity at TACC is really with our life sciences area and the computational biologists. Admittedly, these have been a pretty small consumers of HPC cycles at TACC, back 10 plus years ago. Even though they needed a lot of computational resources, a lot of times when we talk to the biologists, we just didn't have the tools and they didn't have the knowledge to run on HPC environments. They aren't like a lot of the scientists and engineers that get introduced to computational methods while they're in school, or maybe have some introduction to it through their engineering or physics classes. But these folks, they have insatiable demand for cycles. They need tons and tons of cycles to be able to run their things. So what we've done at TACC is we've basically given the computational biologist community access to the biocontainers repository. This is thousands and thousands of pre-built container apps already made for the computational biologists to run their very actually complex workflows. It's not atypical for a computational biologist to be running 5-6 different applications inside one little workflow. And so far, just at TACC, we've had users pull down 3,248 unique packages from the biocontainers and made their own modifications so that they have 14,381 different module file images downloaded and available on our shared file system, Stockyard, and accessible by all of our production HPC systems. This has been huge. We have had to write some tools to be able to support this and be able to allow users to do this. I've got a couple of links in my slides here, but one useful thing for our point of view is we have this in-user read the docs that actually gives you the instructions on how to build a container and run them at TACC. So it literally goes through the whole setup of starting with your own Docker run, how to build the image, and how to go. The other thing is we provide starting images that users can build from their own containers in. It's on GitHub. It's in our TACC repository. You can pull those images. They're already pre-made, but starting, whether it's Frontera, Stampede 2, or Maverick 2. This way, users can actually have a base point that they can start with. And then once they take that image, they can add their own software layers and whatever tools they want into those images. So we've also deployed and allowed tools that will convert Docker and other images to work at TACC. One of the challenges, and sometimes with these images, is you need to make sure that they have the file system layers that match what's available at TACC, and so that the user directories and everything are available inside the images. And so we have some tools that will take Docker image and convert it so that it can be run on one of our compute nodes. This is one of the things that we see is that there's a growing community of physicists in scientific areas that are adopting containers. I think they're seeing the merits of being able to deploy reproducible environments with specific software versions that they want to use on top of HPC resources and be able to run their applications the way they want. Don't have to rely on the systems people to install and build all the tools and software that they might want to run on our HPC systems. So just to point out, this is kind of the base Docker images we have at TACC. It's a curated Docker images. Basically, you can see that we do support a couple of different MPIs. There's Mvapage 2 with InfiniBand support that you can do on Frontera and Maverick. Stampede 2 uses OPA, so we have a PSM2 version there. And then we have an Intel MPI version. And again, the reason we provide these is so that users already have the MPI layers built into the image that they can start with, and that way they don't have to fight with that and make sure that it works in our environment. So it is important that all of these must be invoked by Singularity Run. You can't just launch the images without using the Singularity run. At least the ones in the star, the Vapid ones can be launched. So let's talk a little bit about Charliecloud. Charliecloud's a little bit different from Singularity in the way that it resides solely in user space and requires really no system administrator build and install. And it provides a user-defined software stacks. This is kind of their goal. What's so impressive about Charliecloud is it's very lightweight. And it was designed for HPC systems with security and performance in mind. I think when I was looking at the site the other day, they said it was like only 800 lines of source code to build it. So there is one minor system change you have to make to be able to support Charliecloud, and that's to enable max user namespaces. Normally the default in current Linux environments, or at least the CentOS 7, is to have no zero set to 0. We modified our own local TACC control that we use to support up to 2,000 namespaces. And we only did this on the compute nodes. Again, we don't want people running images on the logins. And so on the logins, we still have it set to 0 so that they can't launch Charliecloud there. But on the compute nodes, we did set it up to 2,000. This one's not quite as widely used at TACC. But honestly, since users can install and run it themselves, they could be using it without our knowledge. And so it's not something we've gone and looked for or pursued. We have had a couple of people inquire and submit tickets about using it, and we've given them some instructions. So we're aware that at least a handful of folks are out there using this on our systems. Now, of course, in both of these systems, the main aspect from our point of view is to ensure that we're not losing performance. And so I've got a couple of slides here that we presented at Supercomputing last year from a colleague of mine, Amit Arula at TACC. What we're doing here is we were trying to measure micro benchmark performance, ensuring that we didn't see any overhead of the containers when we try to run MPI applications on this. So if you look at for pretty much the dots line up on top of each other, it's almost minimal overhead. We do have an exploded view of down here where you can see the very smallish area. And you do see that the Singularity does have a little bit more overhead, the red triangles, but Charliecloud definitely runs basically as fast or even faster in a few cases as native in terms of latency. And really the key is here that we don't see any impact on MPI performance for broadcast in these environments. Similarly for all reduce, we did the same performance measurements of all reduce. And again, at small messages, you still don't see very much performance variability, and it's pretty much almost right on top of each other at the large message sizes. And again, this was going on and running on 4,000 nodes of Frontera at one time, using the Cascade Lake processors and HDR InfiniBand. Now, what this doesn't show is this is the actual MPI performance. However, there's some significant overhead that can happen when you actually do launch your container at large scale. And this is one area where Charliecloud definitely has an advantage over Singularity. In this case, we're looking at the total time to actually run the all reduce application from beginning to end. If you look at the native, pretty much we can accomplish the launch and run in less than 20 seconds. But if you then run on Charliecloud at 2,000 nodes, you see a little bit of performance ability, but that increases significantly when you're going out to 4,000 nodes. And again, most of this is the overhead of loading the images onto the compute nodes and getting them initialized. It's much faster to start up the native executable itself and not have to load all the image layers from the files. So, however, if you look at the startup times, well, it's a minute or two on 4,000 nodes. If you're running for 24 hours, well, that amount of overhead is very minimal when you think about your applications running for an extended period of time on the systems. So to check application performance, we chose Milk. This is a QCD code, very memory bandwidth intensive, does consume a lot of time on TACC systems. What we're looking here is the actual time for solution of the solver on different node counts, starting with 324 and going out to 1296. Again, what we're looking at here is kind of what the overhead is running between straight NVFH2 native versus Charliecloud and Singularity. And again, we're talking about a few percent overhead, and even less at larger scales when you're more network dominated than you are CPU dominated. So, but again, losing a couple of percent to get the flexibility and portability that containers can offer. We tend not to like to lose that much percentage in HPC, but 1 or 2% we can probably tolerate. So, but again, it's important that we don't see a huge amount of overhead like we would typically see on a virtual machine if we were running in that type of environment. Again, we did total time, so this included the actual launch time as well. And you see that the overheads for Singularity do increase more than they do for Charliecloud. So if you just run for, in this case, it was about 2,000 seconds on 324 nodes, you can see that, you're going to spend about 5% more with running your application from end to end versus just, like 2 or 3% performance difference of just the application running itself. So again, these are somewhat tolerable. We do hope to see these improve with time, and we know that the teams are certainly working to ensure that these containers and these environments do support some of the newer technologies, accelerators. The containers have NVIDIA and ROCm support, so that CUDA and ROCm are available in it. In fact, we do have support for running GPUs, and it's described on that read the doc system of using GPUs at TACC within containers as well. In terms of memory, this is another aspect we want to make sure is, once we're launching the jobs, we want to ensure that they're not consuming a lot more memory per node. And in this case, if you look at the overhead in terms of memory, it's very minimal for both Charliecloud and Singularity. For us, that's fantastic. We want to make sure that the applications have access to all the memory that they can, and that none's as little is being used by the runtime environment as possible. So I want to talk a little bit about kind of the future and how we're going to be able to support containers on HPC sites in the future. And Podman is currently under development, but this is really a rootless container build environment. And this allows users to build container images on HPC systems. This is something that we could then start allowing people to do in interactive development queues or things like that, where users can get that access to their node, they can build their container images, and then run them on the HPC systems. They don't have to upload them to some repository and then pull them down and convert them and get them to use on the system. The downside on this one is it really requires newer kernel features like cgroups version 2 and user space fuse to support Podman. And so this is still an area under development. We've deployed it at small and scale environments because you need to have a newer Red Hat versions or CentOS versions. I do want to emphasize Podman actually is somewhat sanctioned by Red Hat, and they are assisting with some of the development of Podman. So this is part of their kernel, not some side project like Singularity or Charliecloud. With our little virtual setup that's similar to actually our Stampede 2 configuration, we're seeing about 5 to 10% overheads at the micro benchmarks level. Now, these overheads actually may be result of the fuse overlay layer, and we're still investigating this. This is still something we're trying to confirm that where are we seeing this overhead and what's causing this little bit of more performance hit than we see with other containers. But we think this will be addressed, especially as developments continue on Podman. Now, I mentioned standardization. This is something that I think as an HPC communities, we can start to adopt and maybe help in terms of the container standardization. There's the Open Container Initiative specification for images. Basically, this is a community-driven image conventions based on the Docker files 2.2 format. Most of the modern container runtimes can build and support the OCI specification. All OCI specification images can be run in all the HPC container runtimes, whether it's Singularity, Charliecloud, Shifter, Soares. And these OCI images can be stored in a lot of container registry services like biocontainers and everything. So, but what it allows us to do is maybe put some labels and put some conventions on these containers so that we can give proper notation, specify, hey, this container used this MPI version. You need to make sure you have this glibc version. Oh, and then you may need to make sure that it was built with this optimizations or this platform in mind. And once we can add these labels and notations into the containers, then it may help the end users be able to pick and choose and make sure that they're pulling in or they're getting the container environment that they expect. So, and with that, I'll just summarize real quick. You know, the biggest benefit from an HPC environment point of view is that containers can provide flexibility and portability to our users. Something that has not really been an option in the past. And in all honesty, it relieves some of the burden of the system administrators from constantly trying to keep up with the software versions and deployments. You know, we can you know, allow the users to run versions that we don't necessarily support on our systems. It may make support a little bit more challenging when the container doesn't work and we have no clue how it was built or anything. But you know, that's something we're going to have to tackle moving forward. You know, and what we can do with containerization is we can actually take these very complex HPC applications and kind of hide a lot of that and put it in there. And once we put it in a container, we don't see these significant overheads, you know, compared to bare metal. We don't see any security issues with running these in HPC environments, and based on our you know, performance validation, even scaling up to 4,000 nodes, we really don't see significant overhead with benchmarks in these environments. And so, so it's something to keep in mind. You know, especially if you have users who are coming to you and say, "Hey, I need this latest version of this. I need this crazy TensorFlow version. I need this new ML package." You know, certainly consider containers to be a way to support these environments moving forward. So, with that, I'll wrap up. I think there was a question or maybe some chat that came in. Hold on. Yeah, okay, there was a question about overlay. Yeah, we disabled, this was something the HPC folks recommended. And yeah, in the Conda environments, actually, that brings up a whole nother topic for HPC. Okay, can come in handy. I'll have to go back to our HPC folks and talk to them about that. But I'm not sure about other HPC sites, but Python and Anaconda is going to be the death of our port file systems. I don't know. I started scanning. I don't know how many user installed Conda stuff we have installed in our Lustre file systems, but it's got to be almost millions at this point. So it's a bit crazy. But anyway, I'll go back and address this. But again, I'm not familiar with the overlay setup. But again, that was a recommendation from our HPC folks. So, were there any other questions, real quick, before I hand it over to Ron?
I think there may be two in the chat window, Tommy.
Oh, okay. Let me pull up the chat. Chat's not up. Another question came in from John. Hey, John. We have not investigated deploying containers to support an inference service. That's something I'll have to go pursue back. Again, I have to admit, I'm more the guy that builds and installs the system stuff, and not necessarily the end users of a lot of these things. So, And yes, I will make the presentation available, and the recording of this session I think is going to be available to all the attendees after the session. So, but I think the plan is to upload the presentations to the Rice Oil and Gas site. If I'm correct on that, Keith.
Yes, Tommy, I believe that's correct.
Right. I'm still trying to find the chat. My chat ears.
There was one question on, are the biologists running embarrassingly parallel workloads?
Ah, yes, yes. In fact, most of the biology applications are single node applications. However, it's not necessarily embarrassingly parallel. A lot of them are threaded. They're taking advantage of the numerous threads that are available on the platforms. A vast majority are running, you know, what I see typically is Bowtie, Bismarck, what else is associated with that? Yeah, and it's a bunch of independent ones. The nice thing is we've convinced our computational biologists to package these up in so that, you know, they can run 48 instances on our 48 core nodes, and so that they've at least gotten smart enough that even though they're using a single node, they're leveraging almost all the cores in the node, and that's important from our point of view. We don't want to see users only using one core on a node. We want to make sure that the nodes are fully utilized themselves. So. There was a question about, was any work needed to enable a high-speed interconnect? No, in fact, this is one of the nice things about the MPI layer, and that's one of the reasons we created those base images. The MPI it's going to use is actually still on the system level. And so once we install a system level MPI layer that can leverage the InfiniBand and high-speed networks, then you kind of just launch the container images over that network with MPI run. Or MPI exec or srun or whatever the launcher mechanism may be for your system. So, so we didn't really have to do any work to enable the high-speed interconnect. It was just kind of there by default. So, all right, I'm still looking for the chat. My full screen window is blocked.
I think the only other question that came in through chat was asking about Podman, but it came in before you addressed it.
Yes,
so
yes, and we are definitely looking at Podman, and again, this is something we hope to be able to use for people to actually build containers on our systems. The downside is it requires at least CentOS 8, and we just haven't bitten off that yet. I think the next system we deploy is going to be CentOS 8, but again, we got to make sure Lustre works with it. All the InfiniBand drivers work with the whatever version we're going to deploy to. So just haven't had time.
If you were to guess, when do you think you're likely to go to?
Well, we're about to start deploying our next system in a couple of months. So we're going to see how it goes on that, and everything works pretty well. Then we'll consider rolling it back onto Frontera. I think at this point, Stampede 2, we're not going to upgrade to 8. It's got the older KNLs, and we want to make sure that the software layers we've had to build for the KNL still work. So, okay, well, thank you very much. And with that, I will turn it over to Ron. Ron, you next.
Okay, switch to sharing my screen here. Okay. There we go. Okay, so I'm going to talk about containers at Shell, and I'm Ron Cogswell with the Subsurface and Wells High Performance Computing Optimization team. So at Shell, we're very conscious of safety, so hopefully no one is zooming and driving at this moment. If you are, please stop and be safe. Okay, I'm Ron Cogswell. I got a Master in Science from Colorado State, started working at Shell in '97. I've been working in HPC optimization, a RATS team for since 2000. I'm Linux geek, parallel programming, Lustre, containers, benchmarking. A cute little picture of my latest home cluster, which is a cluster hat on Raspberry Pi 4. So how we got into our containers at Shell and where we're going with containers. So why did we start? Well, user requests or developer requests. And Tommy covered the Chroot on steroids aspect of containers, so I won't bore you with that again. The benefits for Shell we were looking for specifically were reproducibility and mobility. Shell's a global company. We want to be able to get the applications to all the users within Shell, whether it's a small operating unit in Brunei or, you know, right here in Houston, where most of our HPC capacity is located. So choices, Docker, and Tommy already covered the security issues there with root and Singularity, Shifter, Charliecloud. We've already covered most of those, so I won't go into those further. But when we started at Shell, we selected Singularity, and the reason was it was widely accepted in HPC and offered the potential for getting commercial support for Scilabs, for, you know, some of our folks that might want that. The security model was accepted by our information risk management when we explained that you're the same user you are in the container as you are on the node anyway. You know, there's no privilege escalation. And I said, okay, we're good with that. We wanted the low-level access to the GPUs and the high-speed interconnect IB and OPA, the fact that it can run the Docker containers that the users were interested in, and being able to spin up instances in Singularity. So we brought it in 2019 with a summer intern project. So we did the basic proof of concepts, and now we're in production with, you know, more than 50 different containers. Some of them are versions that have been improved. So the main uses of containers in Shell is coming back to this machine learning and artificial intelligence. We're getting more and more GPU capacity. Shell has got a large and growing data science team, and actually teams. And one of the main goals with a lot of the data science and machine learning is we want to automate the tasks in geophysics. Geophysicists spend time on high value tasks, and if we can make machine learning help get rid of some of these tedious tasks and QC tasks that they do that aren't high value, it's a win for us. So most of our containers are built off of the NVIDIA GPU cloud base images for TensorFlow, PyTorch. We can get some Jupyter notebooks. Some of our cloud teams out in the seismic data universe we're working with Kubernetes. So we did a little POC last year with LSF has an extension for Kubernetes. It was largely successful from a POC, but there's a lot of, you know, just having Kubernetes scheduler is great, you know, but the problem starts coming in with, you know, Insta.io, Flannel, all the things around Kubernetes just beyond the scheduler. So here's an example configuration for one of our Singularity containers, or bootstrapping from the NVIDIA TensorFlow image. We export our proxies, we update, install the required Python packages, install some local neural net code and an IO package. So that's just a basic explanation. But if you look out at the NVIDIA container catalog where we're basing a lot of our images, they keep growing all the time. There's packages for compilers now out there for compiling your for your NVIDIA GPU. They've got this Merlin flow, which is all about building recommender, and they're basically have, you know, all the way from extract, transform, load. They've got, you know, a very large workflow based on using GPUs, and they love selling the GPUs. And they do support Singularity. They've got instructions on how to do how to pull their containers and use them with Singularity. So it works well for us. So an example of some of the containers that we have in Shell. So one of the first successful ones was a Snap and SnapQC, which is a machine learning project to remove noise from seismic data. The original implementation of the code was used in combination of the LMODs and Python virtual environments, but, you know, it still became a bit of a problem trying to deploy that in other locations in operating units around the world. By building a Singularity container, we've got one file we have to send them, and all the HPC in shell, just install Singularity from the Red Hat Apple Lab RPM repository. So here's an interactive container we built for digitizing old log files from PDFs to make them useful. And then this is my current one that I'm working on for a hackathon about doing this job statistics for HPC jobs that are run, showing, you know, just a bit of EDA information about running jobs from a particular job set and why they're running, how they're running. So coming up, the future work that we're looking at in Shell is OCI compliant registry. We've got looking at Harbor is our current plan. We've got a build system set up for users using GitHub and being able to build the containers for the users, because, you know, it, as Tommy was saying, you can't have them building them on their laptops because a lot of them have locked down laptops in Shell and it's hard to do. When we do move to Red Hat 8, we'll be looking at Podman build for the full rootless, because that's where we want to get to. And we're also looking at trying to make it easier for the non-HPC data science teams and things by possibly deploying a Jupyter hub. And then we're looking at using containerization to be able to upgrade the HPC OS to stay IRM or information risk management compliant, and separate some of these slower developing software packages or commercial packages by putting them in containers that are insulated from our OS upgrade cycles and changing of libraries. So I'd like to acknowledge for the help in this presentation, Ashwini, Satish, Adam, and Foko, who are working with us on our build system and registry for the containers. Noella, Soares, Rich Garfield, my team lead, David Baldwin, who helps us get hardware and renewal packages. It's a great team to work with. So that's it from me. So,
Ron, I think there might be a couple of comments in the chat
okay.
window.
All right. Okay, that's good to know. I'll have to check in on this Kubernetes Flux scheduler. I think I saw that at recent presentation. Definitely, thank you, Bruce. Any questions?
One question just came in, Ron.
Okay. We're still an HPC shop. We do cloud, and you know, that's where we're getting a lot of the Kubernetes from. So we're still struggling with how do we run these cloud applications in HPC and Kubernetes. You know, we're looking at Slurm. We're currently in LSF shop. We're migrating to Slurm this year. So we want to containerize the applications that we can, but you know, it's still going to be a bit of a challenge to get all the HPC applications into containers, and I don't know whether we will in the near future.
Well, I think we're running just a few minutes early. The next item on the agenda was a 15-minute break. So we will go ahead and start the break. But I think given that we are early, we will come back at, let's call it 10:30. So we'll come back 15 minutes earlier than what was on the schedule. And we'll start with Shawn Hall with an update on Lustre. Shawn, are you ready to start back up?
Yes.
Then jump right in. Let's go. Introduce yourself and get started. Thank you.
All right. I was going to turn on my video, but it says I can't because the host has stopped it. So you don't get to see my pretty face, I guess.
Here, I'll
but
turn
I'm-
you on, Shawn.
Okay.
Okay, you should have access now.
There we go. Thanks. So I'm Shawn Hall. I'm a HPC platform engineer at BP. And for today, we wanted to have a short talk about Lustre and features and difficulties and things that we've talked about in the past. But the benefit this year is, well, in past years we've gotten together in this meeting and just talked about all things Lustre and compared notes. But benefit this year with being remote is that we can cross the northern border and bring some of our Lustre friends like Peter and Andreas into our virtual call and have a more direct discussion. So this year I was hoping that instead of a bunch of us saying great things and griping and whatnot about Lustre, we can do that in the presence of the folks who have the direction for that. So we wanted to start off, Peter and Andreas were going to give us a quick update on Lustre features and roadmaps and status, and then we don't have a whole lot of time, but we wanted to see if we can have a conversation, oil and gas community to the folks who are at the tip of the spear for Lustre, and see if we can get a good conversation going. So I'll hand it over to Peter, I believe, is kicking us off. And you're on mute, Peter.
Yeah, I still have my SC20 background on. Just that's the last time I could have used Zoom to present, I guess. But so thanks, Shawn. Shawn, one thing you didn't mention when you gave your introduction about yourself is that you're actually a board member for OpenSFS, which is the Lustre community group. And so that's a user-led group. So I'm involved in that on one of the working groups. I'm a lead of the Lustre working group, which oversees activities relating to the Lustre community releases. But it is, an ongoing organization that is, promotes Lustre and is sort of a central focal point for anyone who has an interest in Lustre. So if you haven't been aware of that, I would encourage you to find out. Now, myself and Andreas, Shawn has suggested that what we did was just have a brief, quick whiz through the sort of topics we might cover normally that could be of interest, and then leave most of the time allocated for question and answer. So, so jumping in, so Andreas, because we're going to switch over halfway through this unified deck, Andreas is going to drive the slides, and I'll just talk to the first several and then hand over to Andreas, and then we'll keep back to questions. So feel free to speak up, in chat or whatever. I think there's encouraging for questions as they come to your mind, and then we'll try and work through all those at the end, I think. So Andreas, if you can move on to slide 2 first, please. Okay, I am not seeing, has that moved on to slide 2 with the, I'm seeing a presenter view, but still seeing the title slide.
I see the first slide, not presenter view.
Okay. So
maybe switch screens.
Yeah. So Andreas, are you able to move on to
Are
the
you
next
able
slide?
to maybe reshare the slides?
Yeah. Yeah, oh, here we go. This was our slick format. All right, good. So first of all, are you
able to put in presentation view?
I mean, Andreas is sharing and doing the slides. So
sorry, I was trying to do it, and it's kept on saying your slide sharing is paused. Can you see that or no?
yeah, I can see that now. It's on the
Okay.
right. Yeah. So basically, this was data I sort of put together last year. So unfortunately, last year was a bit of a different year for everyone, but it was a significant year. That it was a 10-year anniversary for quite a few very significant events in the Lustre world. So it's the 10-year anniversary of the formation of both of the Lustre community groups, both OpenSFS, we already mentioned, which is the global organization, and EOFS, which has a slightly broader remit than just Lustre and is focused in just Europe, but is also involved in Lustre community activities. And so at that sort of point 10 years ago, that was when the Lustre 1.8 release came out, which was a very widely adopted release. At that point, because there was a fairly high bar to contributions to the Lustre code base, for the large part, nobody would be willing to sign off all this legal paperwork to go through the hoops to actually contribute code. And so the Lustre 1.8 release, every line of code in there was from Oracle, who were paying their core Lustre engineering team at the time, after acquiring Sun, who had acquired CFS. And so at that point, from then onwards, we've seen a sort of more community-oriented focus, and a lot more different organizations have been involved. Some have come and gone, some have bought others. But we've just seen over the years here, you see all the releases over the 10-year period. And you can see numbers of developers and organizations sort of fairly active and sort of obviously very diverse. And then if you compare, that first 10 years where it was mostly just a single organization doing everything, we've had 45 distinct organizations as of 2013, which is probably closer to 50 now if I sort of double back a bit and factor in the latest release that just came out last month. So moving on, Andreas, to slide 3.
Are you getting that?
Slight lag here.
Are you getting slide 3 now?
I don't believe we are.
It just keeps on saying sharing is paused. Bring your sharing window to the front.
Do you have 2 screens? I think it's because we probably can only see it on one of your screens.
Okay. Darn it.
When you also share your slides, you're able to share just the application window, or you could share your...
Okay, I did fleetingly see it there.
Yeah. Yeah.
I mean, I know what the slide is. I can start talking to it. It's useful for, here we go. So basically, following on the theme of the community, last year was a bit of a different year. Normally we have, a number of events through the course of the year, either specialized Lustre events or, breakouts in, Lustre special focus meetings at larger events like Supercomputing. Last year, everything ended up online. This year and in the early part of the year, it seems that things will be the same. We've had a call for papers for the Lustre user group, which is usually somewhere between April and May, and there's a call for papers that's closing, I think, this coming weekend or maybe Monday. If you're interested in submitting that will be was originally going to be hosted by the University of Florida, and now they're involved in the organization, but it's going to be an online event. Similarly, ISC 21, ISC 20 just got cancelled altogether. By ISC 21, there is going to be a Lustre-based BOF there, that the agendas, they haven't, it's confirmed that Lustre, there will be a Lustre BOF, and there is an agenda formulated, but they haven't fixed down the exact time yet. And then we're hoping, certainly Supercomputing, it looks like they're planning to have an in-person event, and so there's a prospect of having an in-person Lustre BOF there. And maybe some of the regional Lustre groups like in China, Europe and Japan may be able to be in-person events. And then finally, I wanted to draw attention to this, the graphic here at the bottom right of the corner with the So this is data that I've been compiling back since we were at Sun Microsystems and looking at, analyzing the top 500 lists as they come out, and, talking to the people involved in the sites and working out what file systems were being used. And so this is one of the things that I think is, related strongly to that previous slide where you saw the diversity, and basically people are able to use Lustre in different contexts and maybe in different storage offerings for a basis for what they're doing. And so you actually, the people who are using Lustre on the top 100 of the top 500.org lists is actually fairly consistently, the majority of them over a 10-year period, which I think is, very impressive. It shows, speaks to how well Lustre will cope at the sort of most demanding scales, and also just like how, people appreciate the versatility of being able to work with it, in different contexts due to the permissive license. Okay, so moving on to the next slide. Oh, that's better. Okay, so and then we've got going into some more specific news here with recent releases. So we've for recent years we've been doing my sort of team has been producing releases for our customers, which are designated as long-term support releases, and those are promoted ahead of time of what we're doing in the community. And so even people who have different competing Lustre solutions will use those, standardize on those, and it becomes easier for people to have heterogeneous environments, and basically people who are using Lustre open source and want to try it are able to do so more readily and just feel confident that this is an obvious one that they should expect to just work well. And so with these, we aim not to introduce new features, but just to kind of keep up with the latest Linux distributions and versions of Mellanox, etc., so that they will work for most production purposes. We did just the most recent release came out just late last year, 2.12.6, and it just so happened a lot of Linux distributions had their newer versions drop around that time, so that worked well. And then probably through the course of the year we'll have some additional releases as need tells. But you can see that this has been something that's been very widely received in the community. This graphic on the right here is from the OpenSFS annual survey, which just closed last month. And so we've been running that again for about 10 years every year, and doing year-on-year comparisons, and it helps us with planning for future releases and where we prioritize our testing efforts, etc. And you can see that what we've seen there, as one of the things we look for is what versions of Lustre people are running in production, and you can see that this is actually a sneak peek of the data from the 2021 survey, and you can see here I've ringed the two, the last LTS release and then the one that we've had for the last couple of years, and you can see that there are people running other releases. Obviously people have specific features or whatever they're interested in, but we've definitely seen a trend over the years since we've had this LTS stream concept that the numbers have coalesced and around those LTS releases. So it's definitely been widely adopted. And so there are always discussions around, what the right time would be to switch to, a newer release, and then have newer features with all those benefits of bug fixes, etc. And there's always a sort of trade-off between, stability, people who are interested in new features and people who don't want the disruption of moving to something new. So an extra complexity in that conversation at the moment has been the recent conversations around the plans around CentOS and how things will be changing there. That CentOS is definitely widely used in HPC circles. And so that's really something that we're trying to sort of understand a bit more completely about with, what people are going to do longer term if their current usage of CentOS is going to have to change. So as a, doing a bit of an experiment here. So I did have a, I don't know if I'm, oh, here you go. I could do an option here. So I created a mini survey, which is basically a subset of the OpenSFS annual survey, mostly focusing on versions and Linux distros. And I'm hoping we can, you know, all the same caveats apply to this that apply normally. There's nothing identifiable. You don't get spam. It's really just about trying to get a sample of people's sort of usage and interest. And so I've scaled that back a bit. SurveyMonkey thinks it should just take 2 minutes to complete this. So if people who are using Lustre are willing to complete that, that would be helpful and help, you know, input into the discussion. And I appreciate some of you may have already answered the overall survey, but this is an interesting, you know, focusing on the oil and gas sector, you know, a different, we know that's a very important segment for Lustre usage. So it'd be interesting to get some, you know, different data points from this group specifically. Okay, Andreas, can we move on to the next slide? Okay, thanks. And then the other big news is it was actually mid-February, we had the 2.14 major release go out. One of the big things here is we switched, and obviously these decisions were made some time ago about the distros we would support and test through the whole release cycle. So we did, you know, focus our testing on Red Hat and CentOS 8.3 for server point of view, which gave us, you know, newer kernel support. But of course, maybe now in light of, you know, while some people are using Red Hat, many people are using CentOS and maybe disinclined to want to switch to a release using that. But it does introduce some new features like client-side data encryption. So in this version, it's the data itself is encrypted, leveraging, you know, kernel mechanisms to do so. And in a future version, the actual file names itself will also be encrypted. And then we are still in planning at the moment. There's some features have landed already for 2.15, UDSP, which is a multi-rail LNet feature where you can, I'm forgetting the exact details, but
you can fine-tune the routing on your interfaces and such.
Yeah, with multiple interfaces, yes, you can determine which ones for priorities. So at this point, I'm going to hand over to Andreas and to pick up the baton and carry on with presentation.
Yeah, so I'm not going to cover all of the various different features. I thought I would focus on a few features that would be of most interest to the audience here. You know, there are videos from me available from Supercomputing and other conferences that cover, you know, all of the features in depth, or more depth at least. I think one of the interesting improvements in the 2.14 timeframe and moving forward is that we're increasingly focusing on single client performance. And one of the reasons here is that clients themselves are getting, you know, more and more powerful compared to, you know, past years. Used to be, you know, you'd have 1 or 2 cores and, you know, that wasn't a big deal. Now clients have, you know, 96 or 128 cores, and then you get things like DGX or A100 clients, you know, they have 8 InfiniBand interfaces. And so leveraging, you know, all of that bandwidth becomes increasingly important. And you can see here, you know, we've done things to parallelize read ahead, even from a single user space thread to get good improvements there, better strided read ahead. As well, there's been a bunch of work that's started for asynchronous I/O. And so that works with libaio on, you know, kernels going back for many years. And in newer kernels, 5.1 and later, there's a new interface in the kernel called IOU-ring, which is essentially a asynchronous I/O interface that is not really POSIX related. And so what it lets you do is submit I/O requests and, you know, get completion events afterwards. And so your application doesn't necessarily have to wait on the I/O to complete. It's a different kind of I/O model, but it shows very good performance improvements. And moving ahead in 2.15, we're going to continue improving those newer interfaces with mmap read ahead, because the kernel submits mmap reads, at 4K page size, but we can do some limited prediction of IO patterns for mmap, and that's reduced the latency quite a bit. And there's quite a number of improvements that are pending for ODirect, and this helps with DD or single file read write that are doing large IOs, so that you can submit the IO in parallel, and then optimizing that code path. And we're getting pretty amazing numbers, up to 10 gigabytes a second for one client, which is great for both read and write. And another trend in the storage space is the size of disks are continually growing, and it's a little bit of an eye chart on the side here. I have this graph available in full in my supercomputing talk, but it's showing the trend of the top 10 systems, let's say, or top 5 systems by year. And so you can see, storage capacity is increasing, network speed is increasing. What's interesting is that, at least for the regression lines that we did with the top systems, that the Lustre capacity and performance is actually growing slightly faster than the storage unit sizes and network speed. So that's good. It means that optimizations in the software are keeping pace, at least with the available capabilities. And so, we're having 18 terabyte drives this year. And the other factor is declustered RAID helps with RAID rebuilds. And so now, instead of having 8+2 RAID, we're getting 50 or 100 hard drives in a single storage pool. And so that's driving OST sizes into hundreds of terabytes, and we've been testing up to 1.2 petabytes. And so this means that one OST today is as big as the whole file system was in 2006, with that used to have like 1,000 OSTs. And so one of the big deals with having such a large OST size is FS check time. We've done actually a bunch of other improvements in terms of reducing mount time and things like that, improved allocation for large OSTs. But this is one highlight here, is that we made a parallel FSCK. And so you can see the bright green bar is the pass 1 scanning, which is scanning all of the files in the file system. And by parallelizing that up to 128 threads, we get, or 256, we get up to a 36 times reduction in the scanning time for the phase 1, pass 1. And the cyan bar at the bottom is pass 5. Oh, actually I have that reversed. Sorry, pass 1 is the cyan bar, and pass 5 is the scanning of bitmaps and making sure all the allocation data is correct. And both of them have improved significantly. And Amdahl's law, says that the slowest part needs the most optimization. And so now we've done the parallelization of pass 1 and 5, which helps the file scanning. And now pass 2, which was formerly a small fraction of the overall time, is now the biggest part. And that is future work, but we've got at least a 10 times speed up in the overall check.
And I think it's worth saying here, Andreas, right, that you don't have to upgrade your Lustre version to take advantage.
Yeah, that's why it says 2.14-ish as the version, because this is actually E2FS progs is independent of Lustre itself. And so you can get these improvements just from the E2FS progs itself. Another interesting area, I think, is with the reduction of flash cost, having flash file systems is interesting. And on the eye chart, the scaling graph, one of the largest systems today is the NERSC Perlmutter system is all flash, with 36 petabytes of flash, but not everybody can quite afford that. So, one of the improvements that we're working on currently is persistent client cache. I mean, it started landing in 2.13, and we're continuing work on this area. This allows you to leverage flash storage in the compute nodes, and so you can configure, a flash device dedicated to PCC, or use just a subdirectory of an existing flash file system to cache files locally. And so the good news is that once the file is copied into the flash and it's opened by the application, it's transparent to the application, so the file stays in the normal Lustre namespace, but it's accessing a copy of the file that's stored in the local cache file system. And so it's totally transparent. You can do all of your IO locally. It doesn't talk to the main file system after open anymore. And there's different mechanisms for pulling files into the cache. Obviously you can do it explicitly by user request. You can do it in your job launch scripts. There's also a policy language that can be, language may be a bit of a strong term, but there's policy rules that allow you to auto fetch files on open based on user ID or project ID and the file size. And so that makes it fairly transparent to users once it's configured. And so this is leverages the local storage without a lot of management. And of course it's cache coherent with copies that are in the global file system. So if files are cached, it's mainly intended for read-only files that are larger than the RAM size or that are frequently accessed. And but if those files get modified, the cache copy is invalidated, and then you access it from the global file system again. Another new feature in 2.14 that Peter was mentioning is encryption at rest. And so we're using the Linux fscrypt functionality because we're smart enough to know that we're not smart enough to invent our own encryption. And so this is using, uses AES in the background and hooks into the kernel key ring to manage keys. And, the data is unencrypted when it's in the client memory, but if it's written to the servers, it gets encrypted on the client, and the servers don't know the keys. They only see the encrypted data, and then it's when the data is read back, it's decrypted on the client. And there's a multi-level of encryption. So there's a master directory key that is itself encrypted with user keys, and so you can have multiple user keys for the directory key. And then the directory key encrypts a per file key, and so each file has a different encryption key, so that once you delete it, that file is securely deleted. You don't have to overwrite the data, and this can be configured on a per directory basis. And so it's quite flexible if you want to have a subdirectory that's encrypted with sensitive data. It doesn't have to apply to the entire file system. So one of the other features that's been under development in Lustre for a number of years is storage tiering. And so the file level replication allows mirroring of files. And, we've been working on DDN hot pools, which is an implementation of cache management using the file level replication. And so you can do, set up your file layouts so that you write into a flash pool that's, global OST pool. And then in the background, you have the hot pools agent, mirroring the files into the disk pool. And then as space becomes constrained in the flash pool, it will automatically release the flash copy of the file, and you can still access the data directly from the disk pool if you need to. And if you have, large streaming IO patterns, some files can be placed directly into the disk pool if you want. It's not a flow through cache. If you want, you don't have to write everything into the flash pool first, but it allows leveraging both flash and disk directly in the file system. So with that, we're open for questions and discussion, I think.
Well, Keith, I think we got you back on track time-wise.
Actually, that was perfect. I'm glad we had more time. That
Yeah.
was a really good presentation.
I don't know if we got a few minutes before we get back on track. If there's any audience questions, one just popped in, we can talk about that, or vice versa. If Peter and Andreas have anything they wanted to ask the oil and gas community, this is a great time to do it.
Looks like one question came in about Lustre on ZFS.
Okay. Yeah, so there's still, ZFS is definitely still supported. At DDN, we're focusing mainly on LDiskFS, but definitely there are, still major players with ZFS. Lawrence Livermore is, continuing to be the key developer with OpenZFS, and that community is very strong, and they, we still test with ZFS for every patch and every build of the community Lustre, so it's not forgotten by any means, and there's a lot of development in that area, just from the ZFS community.
For example, the Lustre 2.14 release that just came out is supported the OpenZFS 2.0 version, so there's definitely activity there. And I believe, I don't know if it's in the public domain, so I won't name specifics, but I believe there's a couple of very significant, large deployments that will be Lustre and ZFS based that will be announced in the coming year ahead.
So there's a new question. Is the automatic storage tiering a feature of Lustre or a specific implementation that DDN offers? So it's a bit of both. The file level mirroring is a feature of Lustre, so all Lustre clients support that. It's starting in 2.12, I think, and the part that's DDN specific is the tier management, right? And so there are other implementations of cache management software available. The hot pools stratagem functionality from DDN is specific to our implementation. All right.
Well,
So I will promote the plug the survey again that's in the chat. There's six people have responded already by the look of it, and it says it took them 2 minutes. So on average, so it's not a big time investment, and it would be useful. So thank you for that. Okay, are we ready to hand off to the next presenter if there's nothing else?
I think so. Thank you very much. Noella?
Okay. I try to share my screen. But it will not let me.
You are listed as a co-host, so you should be able to.
Let me see if this works.
Yes, we see that.
Okay. For some reason, it won't let me share my video. I'll get started. All right. Hi, I'm Noella Soares, and I work as an HPC engineer at Shell. I've been working at Shell for 22 years in different roles within the HPC group, including running the data center, the HPC data center. So I'm going to talk about PGFS on NVMe, more specifically beyond. So the reason I put the first bullet is because our customers are really happy. Sorry, it's gone to the wrong one. Because we've been able to solve the noisy neighbor issue for them. So one of the biggest concerns of running an HPC workload on shared resources is the reduced performance due to a noisy neighbor. But applications that run on beyond are not noisy neighbors, and therefore they do not disturb users of the parallel file system. So compute nodes are often equipped or can easily be equipped with internal hard drives. But the problem with this is that they provide neither the advantage of a single namespace across multiple machines, nor the flexibility and performance of a shared parallel file system. So every compute node can have a local NVMe drive or multiple drives. And all the drives are pooled for use by the cluster. Beyond creates a shared parallel file system on a per job basis across all compute nodes that are part of the particular compute job. And it does this for exactly the runtime of the job. So the PGFS parallel file system was designed for I/O intensive workloads that require performance and capacity scalability. So this ability can be used in many different use cases, but it was especially to create temporary work file systems. So Beyond is typically used to aggregate the performance and capacity of internal drives in compute nodes for the duration of a compute job. This provides additional performance and a very elegant way of burst buffering. Beyond also supports all TCP/IP based networks. So PGFS is open source and is maintained by our HPC team without any third-party dependencies. And it can be downloaded and used free of charge without any limitations. Because we can use our internal drives, we reduce rack space in the data center and also save on power and also cabling. So what makes Beyond so effective is that it was developed to create one or more instances on the fly, and Beyond can stop and start these PGFS instances with just one single command. So due to the very simplified startup it is easy to integrate beyond with job schedulers, workload managers, such as Platform LSF or Slurm. So as stated previously, Beyond can start and stop new BGFS instances with just a single command. So you can easily add it to scripts to start when a compute job starts and stop it when it is finished. Beyond can simply create a new mount point. Any of the standard tools like copy or rsync can be used to transfer data into and out of Beyond. But Beyond package also contains a parallel copy to transfer data between Beyond instances and other file systems, even maybe your persistent global storage. So to operate Beyond, it needs the PGFS server and client components. Therefore, the respective packages are set as dependencies and will be installed automatically. One thing you need to make a note of is that the Beyond package is installed on all hosts that are part of the PGFS instance. So Beyond also supports the utilization of storage pools. It is able to automatically create multiple targets on all involved hosts and assign them to pools. So NVMe is an industry standard software interface that enables SSDs to run directly to the PCIe physical interface on a motherboard. This allows SSDs to act more like the fast memory that they are, rather than the hard disk they imitate. NVMe also has access speeds up to 100 times faster than a traditional hard disk. And we benefit from the lower latency and higher performance. And because of this, our existing NVMe drives can now be used as temporary job directories or rat space. Beyond provides a very easy way to remove I/O load and nasty I/O patterns from your persistent global file system. Data created during the job runtime can be moved either to your home directory, project mounts, or your global persistent file system. Our customers also appreciate this consistent potential, higher performance file system, even though there are some reductions of available compute and memory per compute node. We are able to use the internal compute node drives, which might otherwise be useless for many distributed applications, into a shared parallel file system. So Beyond does not add any new cost for servers because we can simply use our existing compute nodes. And you can benefit from BGFS even if your persistent global file system is not based on BGFS. And of course, the best part for us is that it fixed the noisy neighbor issue. Any questions?
Noella, thank you very much.
Thanks.
And would love for you to stay around through the panel discussion in case other questions come up.
Sure.
We have received one question in the chat. No, the question we got was,
Yeah.
what hardware are you using for your HPC?
So we use a variety of hardware. Ron, can you?
We try and keep up, with the trends. We're using Roam nodes now, and we've got a couple NVMe's on each Roam node, but it's always a price performance issue, and it always goes right through David Baldwin's team, so he can tell us why.
Says we use a lot of Roam nodes at the moment. We tend to use whatever is for best.
David, I can't hear you.
Sorry, I was on my wrong headset, I think. Is that okay?
That's great.
Yeah, so we like Ron said, we use a lot of Roam CPUs at the moment. We tend to use whatever is the best price performance, so either Intel or AMD primarily. I don't think there's anything particularly strange about what you do. It's a sort of normal machines you would just find in any HPC. It is optimized for price performance, so we tend to throw quite a lot of memory and disk into our nodes just because that's how our algorithms seem to like to work. So.
Well, good. I think let's hang on to any other questions for the open panel discussion. Let's turn it to Kent, Tommy, and Ron to give us an update on water-cooled systems management.
Hi, I'm Kent Blancett with the high performance platform team at BP. And here's what I want to talk about a little bit today. Very simple. BP has had a couple different forays into the liquid cooled computing systems arena. One back in about 2010 to 2013, we had a couple racks of IBM Power 6s. Those were 80 kilowatts a rack with rack CDUs and rear door heat exchangers. We had a few issues, like with most things we try. We got around them, but there were a number of leaks and pump failures that had to be worked on. Then again, in our new building, starting in late 2019, and we've had 3 different acquisitions of Cascade Lake APs that are all hooked together. We're now up to 2160 HPE Cascade Lake AP nodes. These are about 62 kilowatts a rack, and it's using what's called, company name is Cool IT, and they do direct chip cooling. We use 6 of their end of row cooling distribution units, and they're in-rack manifolds that distribute all that liquid into the compute nodes. Benefits we see are we can get a higher heat density within the computing space. Our computing space was designed to handle 35 kilowatts a rack to be cooled with air. But since we're over that, we have to use some sort of liquid. These systems are cooling or removing about 75 to 80% of the heat that's generated through the liquid. And this is from the CPUs and memory. The remaining heat is not done through liquid. It's still coming out through the air. This includes heat from the power supplies, the NVMe drives, NICs, motherboards, and network switches. Benefit is you got less noise in the computer room, which is a whole lot nicer for working in if you have to be in there. We hope it will increase the lifespan of the machines, and it saves money on cooling. Like with everything we deal with, we run into issues at the scales we operate. So, a small issue is not something we're going to be terribly concerned about as long as we can get it fixed reasonably. We have had 3 minor issues, and over the span of this cluster, which is roughly 1,000 node years, we've had 3 small issues. During initial installation, we had 1 small drip out of a water connection, and that was easily fixed with just tightening it up. We did have a minor leak from an automatic air bleed valve out of one of the CDUs. It became a little more major, and it did cause a shutdown of that CDU. All the leaked fluid was contained within a catch pan as part of the CDU. And the way we have it designed, the partner CDU was able to handle the load the way it was designed. We did have 1 machine out of 2,000 that has had a leak within the node. The liquid is a glycol-based solution, so it's green. And if you look at the picture, you can see that there has been a leakage over time. And we don't know how long the water or liquid was leaking, but the green around the heatsink was just kind of a gel when we opened it up. We started seeing some, yes.
I don't think you've been sharing anything this whole time.
Well, that sucks. I'm not sure why. But that node is being investigated by Intel and Cool IT to determine what the issue is. So the observations we've had is that the CDU monitoring and controls seems a bit rudimentary compared to most of the computer systems we deal with day to day. The access to the CDUs includes Telnet, FTP. They just recently added tools like NTP so we can correlate dates and times of events. It does have SNMP traps, so that's good. So we have had several failure scenarios that were not handled well by the CDUs, and we've worked with the vendor to alleviate those issues or understand what's going on better with them. And we did have one time where a complete shutdown of all the CDUs happened as a result of some network traffic on our admin network. So we've had to do some more isolation of those systems from other traffic. That's all I have. Tommy?
Thanks, Kent. Yeah, so I'm going to give a quick little update on Frontera and our use of liquid cooling on Frontera. Hold on, let me just share my slide here. Okay, hopefully I'm not going to go into presentation mode. I'm just going to show you the slides here. So I just wanted to give some context about Frontera and the liquid cooling setup. So like Kent said, we're taking advantage of Cool IT and these CDUs to be able to provide much more dense solutions. In our case, we have 91 total racks for Frontera. There's 88 compute nodes per rack. Each rack has been measured at a little over 60 kilowatts of power when you're running full bore in each of the racks. So to be able to cool that, we pretty much opted that we had to do liquid cooling. What's interesting, and Ken also alluded to this, is we have 3 basically CDUs in the row, and you can see they're on the ends and in the middle. And they are redundant in that we only need 2 of them to run to be able to cool the entire row. And we have confirmed that because we've been able to cycle CDUs out of production to go into maintenance and do preventative maintenance on the CDUs while we're still in production on the rest of the system. So in addition to the direct liquid cooling from CoolIT to the compute nodes, which I'll show a picture of in a minute, we also have cooled doors on the back, and that's what these little blue units on the backs of the racks are. So most of the cooling is provided direct to the chip, but there's also some supplemental cooling. So about out of the 60 kilowatts, about 15 kilowatts of cooling is provided by the cooled doors. The way our secondary loop works is, our primary flow comes into the CDUs. We provide 7 degrees Celsius water to the CDUs. The CDU set points are at 17 degrees Celsius, so they provide 17 degrees Celsius secondary supply to all the compute racks. Those go through the chilled doors first. It goes up about 3 degrees Celsius when it comes out of the cooled doors and gets delivered at about 20 degrees Celsius to the compute node. So very cool, very efficient. We were able to run LinPack 4 bore on the entire system with no issues in terms of the cooling. In addition to the liquid cooling directly to the computes, we also have liquid cooling in each one of the core switches. So we have 6 Mellanox InfiniBand HDR core switches. They are liquid cooled as well. They have their own CDUs that run on them. So we did have to provide additional plumbing to each of these units and each of these CDUs. From the point of view of deployment, our basic role, we had to make sure that we provide primary water into their secondary water loop, and they built and installed all the secondary water loop. We also had to make sure that we had independent supplies for each of the 6 core Mellanox switches. So keep in mind that not only is it liquid to the processors, but it could be liquid to your switches as well. But it's impressive that we're able to get 60 kilowatts in a rack and keep it cool. We started deployment of the system about 2 years ago. System went into full production in July of 2019. So we're almost up to 2 years of production. And in terms of operation on the system, it's been quite reliable and stable. We've been pretty happy with it. We stumbled into similar issues that Kent reported in terms of, the control system's a little bit rudimentary, didn't really account for a couple of failure modes. We've been able to work with the vendors to get enhancements and improvements. We do collect all the SNMP data on it. We have charts, and we actually feed it into our Zabbix so that we can keep a history of all the cooling and what's going on with all the units. And so in terms of leaks, we've had a few leaks. Just to show you what the compute node rack looks like, this is actually what one of the racks looks like. It's a taller than usual rack. It's a 54E rack. One accommodations we've had to do is a little bit wider than standard rack. These are 30-inch racks, and that's so that we can put the liquid cooling manifolds that have to feed every compute node on both sides of the rack. So there's a supply and return manifold on each side of the rack that feeds half the nodes on this side and half the nodes on the other side. The inside of the compute node, actually, this is what one of them looks like. So you can see here, this is the CoolIT chill water loop. It does take up one of the PCI slots to be able to go out. We have an InfiniBand card in the other PCI slot. And here you can see the loop. As Ken also mentioned, we've had a handful of leaks inside the nodes. If that glycol gets inside the nodes, it's very caustic. The motherboards typically fail with some kind of voltage error or voltage fault. So we have had a handful of nodes that have had that, but out of 8,000, it's been pretty minimal. And I think the feedback and improvements that we've seen, a lot of the ones that have failed back to Dell and CoolIT team for failure analysis. And I think the enhancements they're doing now are going to definitely address the issues we've seen on site. So one interesting thing, Kent didn't mention this, because you do use that ethylene glycol solution as your secondary fluid, it glows in black light. So we use black lights to go find leaks now. So one thing we have to do is make sure that if it does dry and we did have a leak, we make sure to clean it up very closely, because next time we come through with the black light and we're looking in the racks, we don't want to find an old leak or something that we stumbled into. So just a little trick we found for operations on Frontera. So with that, I'm going to pass it. I think Ron was next, and if we do have some questions, I'm happy to answer them in our question and answer session that's going to start right after this.
Okay, so I didn't prepare any slides for this. Shell's got a couple of cooling systems coming into production in the near future. One in Amsterdam is immersion based with a company called Asperitas. And the interesting part about that is we actually are supplying the fluid as a shell product to Asperitas. So that is almost in production. I believe it'll be in production in the next couple of weeks. And then we have a cluster coming in May, which has 8 GPUs per node, and that one will be water cooled with CoolIT. It's getting started on the build right now in California. So they're starting to put that. We just moved data centers at the end of last year so that we would be in a data center that could accommodate our plans to use water cooling. David, did you want to add anything to that very short speech?
No, I think I just reiterate one piece that I think it was you, Tommy, said that we're seeing these very, very high wattage loads around the CPUs, 250, 280 on CPUs, 400, 500 on GPUs, and the roadmap just looks worse. It doesn't look better. So I, like Ron says, we've just moved data centers to help us be able to do this. But I think, or maybe it was Keith right at the beginning, but I think this is going to be one of the big challenges that HPC on-premise operators are going to have to really work.
Yeah, I'm beginning to regret that statement I told the vendors, about 5 to 8 years ago. Oh yeah, y'all can continue to increase the power in the socket. That's no problem. We can handle it. They went gung ho on that, went all out.
Yeah, I mean, like Ron says, we haven't actually got our systems yet. The one in Amsterdam is weeks away from production. The one in Houston is coming in pretty fast. So maybe Kent and you, Tommy, I get a little worried when people say, "Oh, a few things leaked," but we just kind of wipe it up and we trashed a couple of $1,000s worth of CPUs. So maybe some thoughts around that. Is it as scary as people really think it is?
Yeah, I mean, I have to admit, we were probably one of the first to do a really big deployment of the CoolIT stuff, and I know that they took some lessons learned. We did have one pretty bad leak in initial deployment. From our point of view, the vendor stepped up and covered any damage and costs, and so they've been well aware. And in the few cases we've had a leak, we try to definitely feed it back to the teams, CoolIT and Dell, to make sure that they can do failure analysis on it, make sure that whatever they're doing now addresses those type of failure modes. Yeah, and all the motherboards get replaced, and they even warranty the processors in case they do get damaged. So as long as the vendors are willing to support it and maintain it, I think that's the most important thing from my point of view.
Yep, a good warranty is pretty important. So
at the scale we're operating, we're bound to run into some issues.
Yeah, exactly.
And I would agree that I don't see us ever going back to air-cooled systems for anything large. When we
I'm trying to actually
to
leverage some older data center space where I'm trying to weigh the options, and it's it's going to be tough going back to air-cooled just because I can't get the densities I can now get with the liquid cooling.
Hey,
I was surprised. Yes.
What's the highest power per rack for the air-cooled systems you have?
We have some that are 32 kilowatts, and those are hard to keep cool. We had to do a lot of work with extra insulation and things to keep air from backflowing in the racks and doing all kinds of things that would create feedback.
So
and I think in Shell the highest air-cooled rack we're running is about 38, so pretty much the same, and it does get pretty hard.
Any potential issues in terms of degradation as you get closer to the 3-year lifespan? Ken, I think you're seeing some problems that are kind of a little scary with air-cooled.
We know that we have issues as you get things like the fans in the computers, those are running much hotter or much faster. And it's a rotating part. It's going to wear out. And we do have more fan failures, hard drive failures, depending on where they're located in the rack. Memory is probably not terribly bothered. The heat sinks on power supply, on the CPUs themselves, those have been a real problem. We have some that have internal corrosion where they do their internal heat pipes. So there are issues with air-cooled systems and running them as close to the limits as we do.
Yeah, I wouldn't say in Shell we particularly notice that. As nodes get old, they get harder to maintain. That's just true. I think one thing I'm interested in as well, beyond the obvious thermal problems with trying to keep densities up and all that, is will liquid cooling give us a bit of stability on how the chips go to different frequencies. Obviously, if you're trying to put a 100 node job and maybe you've got a 2.5 gig processor, but really it's somewhere between 2.3 and maybe 3-ish on a 100 node job. If one of the nodes is running at 2.3, then effectively they all run at 2.3. It doesn't matter if the first 99 turn up early. So have you seen anything like that, Tommy or Ken?
No, unfortunately, we expected. One thing we do expect over time is that we'll have better reliability potentially of the chips. We don't think they're not going to that thermal cycling constantly, where they're going to a really high temp and a really low temp. In terms of better performance, unfortunately, we still see the same variability, whether it's air cooled or not. I literally have the same exact Cascade Lake nodes that are air cooled versus liquid cooled. And we still see the same performance variability. It's a power limitation in the socket for the most part. And it's the processor itself trying to figure out how much it can handle in terms of frequency and power to stay within their TDP limits. And some of the vendors try to make some tricks and do some things to circumvent that. But yeah, we still see the variability. One thing we learned, and something that was interesting from our point of view, Intel actually doesn't want you to keep the chips so cool anymore. Our expectation was like, well, keep the chips cold and they'll run better. They've actually tuned them to run at a slightly higher temperature since most of the stuff has been air cooled. So we're working with them right now, trying to do some studies on, how much are we really losing? It's fractions of a % of performance though. So I don't think we really see it, but my hope is reliability of our platforms will be better. I've seen with, like Kent has, in areas where we've had, data centers where we've run warmer clusters, the reliability of the parts in the 4th or 5th year, especially it's anecdotal. I don't have hard facts on this, but it seems like the top of racks tend to fail more, and that's where it's warmer. So,
we had heard initially that some people were having better performance stability on GPU nodes when they were immersed.
We have not looked into that. So,
so we were hoping for the same kind of performance on CPUs, and we have not noticed any better stability. They still have a lot of variability, and they're more variable than all the previous platforms. So that variability is just increasing. It does not seem to be something Intel can fix.
Well, good. I think we are drifting into the question and answer period. So I'm going to ask everyone on the call to jump in with their questions. But I've got a couple to get started. Would the people that are participating make any comments on how they have managed big computer systems through the pandemic? How did you manage with fewer people on site, more people working from home, bigger demands on remote graphics? How did you pull it off?
I'll jump in here. Well, start. So I have to admit, I was really thrilled that, I've been pretty adamant all along when we deploy our systems. I want our guys to be able to manage them remotely anyway. I'd like to try to run a lights out shop. I don't want to have our guys go into the data center all that frequently. Because we had designed and built a lot of our systems with that in mind, we've been able to manage with pretty much all the sysadmins working from home, including myself. But we do have an operations staff that's on site. Now it's a skeleton staff, they're essential personnel. They were, they got additional testing and abilities that we gave them through the UT since they were part of our essential personnel group. And luckily, with following the UT policies, masks and everything, keeping our social distancing, we shut down our operations center. We don't share that space anymore. Everybody went back to their own individual offices. So our ops center, instead of being the central place where people are monitoring, they're actually monitoring from their own offices now. But other than that, we can pretty much manage remotely. Our big challenge is new hardware and getting rid of old stuff. I got to send people on site, and unfortunately, people, installing equipment and everything are going to be closer than typically, normally allowed for social distancing. And so the good news is most of my team is starting to get their vaccinations now, and starting to hopefully getting ready to be able to go back into work, especially since we're about to start building a new system soon. But beyond that, we've been able to manage things through lights out management and remotely, and lots of Zoom calls.
Well,
Oh, go ahead.
we removed half of our KNL cluster early in the shutdowns and installed 1/3 of our Cascade Lake APs at that same time. And that involved a lot of people physically in the office. We had to put in some more procedures to make sure different vendors, suppliers doing the chilled water installation, and then us, we're all protected from each other and within our own groups. We typically had 2 people on site throughout the shutdown to do hardware break fix, and we have, in total, we've had another, I guess we had 2 installations of Cascade Lake AP during the shutdown. So we just try and keep people separated. We have had some more testing of people that had potential exposures outside of work. And one person did have COVID, but because very few people were around at that time, it ended up not being a problem.
David?
Yeah, I think I can trump that, because we, like Ron says, we actually moved our entire data center, which was probably not the greatest timing we've ever thought of. So in January, we shut down our data center over in Soares 1, where most people know we were, and we've moved across Houston. It took about a year of planning, to be honest, to get it right. And then, of course, COVID happened. We were already deep into the planning. We spent a lot of time working out how to make sure that we didn't have people on top of each other. We had people designated solely to do safety. So we had sysadmins wandering around moaning at people to put their masks on and not stand each other. So, which is probably a waste of their talent and skills, but we didn't get anybody sick. I think in Shell generally we're quite lucky. We have we've run a follow the sun operations system for a long time. We have data centers here in Houston, the Netherlands, India, and Malaysia. So it was not very complicated to just sort of carry on doing that. We do have a lot of tapes, so there is still people on site handling tapes and hardware and things like that. So you just have to be careful.
Any challenges with supporting more people working remotely with remote graphics capability or performance?
Yep, definitely that was a big change. Not so much for HPC because a lot of our user base is not really anywhere near our HPC anyway, so they just kind of carried on. I think for Shell IT, that was a big change to obviously I think we have 80,000 people in the company, and suddenly we went from 5 to 10,000 people logged on remotely to 80,000. So that was quite a challenge. I don't know if we were lucky or not, but we have an operation in China. So we did actually, unfortunately, have a couple of months practice when our Chinese operation went virtual. So we kind of saw it coming, but I think we just got a bit lucky there.
Tommy, anything you had to deal with for remote graphics?
Not so much for us. Most of our problem is the end users. Their desktop, their bandwidth to their home is not always so good. So, but most of our folks use remote PNC sessions and that type of thing, tunneled over SSH, and so so they're being able to do most of what they need to do. Again, a lot of our user base is remote already, and through our portals, our Viz portals, and Jupyter notebook portals, they've been able to interact with that. And but yeah, not too much. Paul and Averett will be able to answer that question a lot more. Okay. He's leading over this group. So,
well, BP went through a corporate change of our VPN platform, and there were some growing pains there. And like Tommy mentioned, home users with Wi-Fi access that may not be really good. We had to do a lot of counseling and suggesting try this instead, move to another room, at least just for a test and see if it works better. And then if that works, you may have to do something different, hard line or whatever. How about questions about what people did during the Texas freezing over a month ago?
Yeah, that was fun. It was fun. We had a kind of a double whammy early this year. New Year's Eve, we took a power hit. I think there was that cold storm came through there and actually knocked out our chillers. The power to the data center actually was fine, but of course you lose your chillers. Things are going to overheat pretty quick. We did learn that our liquid cooled racks will shut themselves off very quickly once they lose chill water. So our fun started New Year's Eve, and then of course 2021 told 2020, here, hold my beer, and, and then we got the big freeze. We were lucky enough we didn't have any damage in the data center. I do know that some other places had some freezing and even their liquid cooling and stuff, and chillers outside froze over and everything. We were lucky that we didn't experience any of that. So no pipe bursts or anything inside the data center. One thing surprising to us is nobody actually contacted us about shutting down. We voluntarily idled everything and powered off all the compute nodes. My understanding is, I guess the UT campus where we're at is considered critical infrastructure. They do run a nuclear facility there, so I wouldn't want them cutting power to them. But we literally dropped our power from typically of like 6 to 7 megawatts operational all the way down to just a few hundred kilowatts. And it was just keeping the storage, login nodes, and only that up and running. We wanted the rest of the folks in the city to have whatever power might be available. Unfortunately, didn't actually help them. They didn't get the rolling blackouts. They just got blacked out. Myself, I actually got kind of lucky. I live right next to a fire station and continue to have power through the whole thing. So I was able to log in remotely, monitor, and make sure the file systems were all still functional and everything while we were shut down.
BP, since we had everybody working remote, many of our people lost power at their houses. So when we actually made the decision to shut down, but we had to do that with a limited set of people that still had power. But yes, we shut down all the compute nodes and kept the storage and network up, just like Tommy said, with the idea we'll give back some to the grid.
Yep, and we did the same. We actually went on to generator power to release all the power back. One thing we found, and this is true during Harvey and previous problems we've had here, often it's quite easy to keep the data center running and we can carry on doing that, but often you don't have the users anymore. They are dealing with family emergencies or whatever. So often we see that it's more of a jobs dry up rather than we can't keep the data center moving. So for something like the recent freeze, it was only a few days, so it didn't make that much difference. We normally have a pretty healthy backlog, but for something like Harvey and Ike before that, you can see it disappear pretty quickly, and then there's kind of nobody around who cares about their HPC anymore, or cares about running their HPC job anymore.
We did see some of that job reduction. We did get some requests from users, mostly remote, saying, hey, is there any way you can bring some of it back up so I can keep running? So we quickly brought about 10% back up, then 50, and then went back to 100 in a short period.
We did have some network issues within between data centers, and lost AT&T for a little while, but yeah, not much we could do about it.
So Tommy, what progress have you made with monitoring systems and application performance?
Yeah, I'd have to go back to Todd on that one. He's been collecting a lot of that data through our TACC stats program, and I know that they've added some enhancements to it to get better fine-grained monitoring of actual performance and what users are doing on the system. I wish I had more of an update for you, but unfortunately, I do know that he makes it available through GitHub. I think it's in our TACC repository that the TACC stats tools are available there. So if folks do want to try to deploy it and get it out on their system, feel free, and happy to take some feedback. Yeah, I have to admit, I've been focused on other things for right now. Yeah, the systems are running and everything. I'm not messing with. I'm trying to mess with new technology. And actually, like I mentioned, we've been trying to get a purchase out for this new system that we plan to deploy in a few months. We got to replace our old Lone Star 5 Cray system. It's already 5 years old and definitely end of life. So
tell us about the new system.
Yeah, so what we're looking at right now, haven't made any final decisions yet, but we're obviously very interested in the Milan processor and from AMD. It looks very performance competitive. Of course, we just got some Ice Lakes in since those also got released, so we're still haven't made a final decision yet on that. So, but the good news is with either one of those, we're doing PCI Gen 4 and straight HDR 200 into the nodes. So it will be more than likely InfiniBand based system as well. Beyond that, I think it's unfortunately going to be a little bit smaller. We don't have as much money as we did when we purchased Lone Star 5. But we're still looking on the order of 400 or 500 nodes of Milan with there's 128 cores in a node now, so it's going to be interesting. And I think we're going to start working more towards node sharing as well, and seeing if we can act, with that many cores in a node. Users are going from nodes that would have 24 cores in it to 128 now. So it's a pretty big jump from Lone Star 5 to Lone Star 6. And so we're going to have to see if we can either share the nodes and how much we can get better, support smaller jobs with multiple jobs per node.
Do you think most of your applications will scale to use all those cores?
Most of the ones that are supported on Stampede 2 and Frontera would. Unfortunately, there's still a large number of Python scripts single, with threads that I don't think they're going to spin up to 128 threads on a core. I mean, on a node, they probably won't scale that far. So that's one of the reasons we're investigating the node sharing. But again, trying to avoid even the problem Noella mentioned about noisy neighbor on the node. It gets worse when they have to share nodes than just the file systems. Then you got contention over the network and shared like local disk or anything like that.
David, Ron, Noella, anything that y'all are doing with monitoring systems, tracking application performance that you'd like to brag about, or any issues that you'd love for the community to help you support?
Yeah, I'll let Ron talk a little bit in depth if he wants, but we have spent the last couple of years really trying to beef up our monitoring using a whole load of I don't know, free tools. It had been quite a weakness on more on the application support rather than, is a node dead? You can find that out pretty fast. I know, Ron, do you want to drop in? I know a lot of the work was around trying to, I don't know, make Lustre behave as well. So
yeah, that's where I spend a lot of time with the monitoring team saying, I want to see this on Lustre. I mean, a couple of years ago when we were up at TACC, we had monitoring where we're looking at the RPC stats for our Lustre file systems, and that helped us find problems with Lustre. And of course, right now, trying to move to, Red Hat 8 and newer Lustre clients and still see issues, and having this monitoring of the RPCs, what's going on the server side and the client side of the Lustre file systems helps us say, okay, we need another patch on the client for this issue. It's this JIRA number. So having that extensive monitoring of Lustre helps us try and move forward, because our information risk management people want us to move OSs forward. And of course, our stability HPC side says, wait a minute, we got the thing working. It's tuned. Don't break it.
Speaking of operating systems, what are your early thoughts on how to manage with the changes going on with CentOS?
We're not going down that road as we're still a Red Hat shop.
yeah, and I probably don't want to broadcast my views about CentOS and what they're trying to do. So
I think you just did.
We're definitely not happy with what Red Hat's doing, but we do have hope that somebody's going to pick up the ball and keep a community environment like CentOS moving forward. It's just one of those things that we're keeping our eye on Rocky. We think the Rocky Linux guys may be able to pull off being able to do this, but we're still in a wait and see mode. But we're going to evaluate. We do run some SUSE. The open SUSE stuff is pretty good now. It sounds like they've done more effort than Red Hat's been doing recently with the CentOS releases.
Okay.
So,
tell us a little bit about your challenges of recruiting and training systems people. What's been successful?
This one's still a challenge for us, and actually, unfortunately, COVID's made it a little bit more challenging because we can't do interviews and have people come on site and do those types of things again. I'm still having challenges just getting folks that have HPC experience, and even when we do hire them and get them trained up, then the industry folks usually come snag them from us, which is fine. We understand that that's part of our role, but one thing I've made an effort to do is start a younger pipeline of folks, that come in as our operations team, train them a little bit on the system side and let them start taking over smaller stuff. And if they show ambition and want to, get out of that role of operations and more into the administration side, I certainly encourage it, and I've had pretty good success with multiple folks going that route. Even one or two that's now been hired off into industry. Intel still owes me a few. They've hired a few of my folks. So, it's still a challenging pipeline. Even at a university site, you'd think we'd be able to get students and everything, and unfortunately, since we don't have graduate research programs, I can't. It's not easy for me to get graduate students and assign them to projects and kind of train them up and get them groomed to potentially come work for us. But, I'm sure y'all struggle with same pipelines for HPC folks, especially.
Yeah, I think it's the same sort of problem. So we've actually expanded in India quite a bit, and we've had quite a lot of success getting some good HPC engineers there. Mainly, and that you probably don't want to hear this, Tommy, but we did to them what we do to you. And once we found out which universities or government agencies, like the weather people, had HPC installations, then we started trying to recruit from those. So it is a little bit targeted, I'm afraid. So.
Well, once the academics can actually start paying what you industry folks can afford, then I might be competitive.
Yep.
Well, I think we've reached our time target. Why don't we let you guys think about any closing statements in terms of things that you're proud of, challenges, and any last suggestions for the audience. David, would you like to start?
Yeah, I think I'm going to go back to maybe your opening slide, Keith. And I think the next 5 years are very, very exciting, very, very challenging. This huge diversity of what are we going to do as an industry, I think is going to keep us busy, happy, excited, awake for quite a long time. So you're probably sad that you're leaving us, Keith, and you won't have to worry about it. But I'm still excited. So,
Ron?
I've got to agree that it's exciting out there, and I get to work with Tommy and the folks at TACC, get to learn some of their webinars and things that went on last year were quite informative, and be able to work with other folks in the oil and gas and have these engineer to engineer conversations is always a good thing.
Kent, Shawn?
I think it's going to be interesting, and I keep thinking of the Run Forest Run as we try and stay ahead of the cloud.
Yeah, I think it's going to be an interesting time to be a sysadmin with all the diversity, all of the just looking at the systems layer, being able to keep up with different processor technologies and different ways of working between clouds and containers and all that. And the other one that kind of popped into head is, at least at the moment, there's several monopolies and duopolies between, who can you buy Lustre from, and who can you buy a high-speed interconnect from, and who can you buy cloud resources from. And there's a lot of sort of concerning shifts in the market that I'm hoping will get a little bit more diversity in them over time.
Noella, any closing comments?
Yeah, I'm excited about all the new equipment we're getting in with cooling and emergent. And so I'm looking forward to working with those.
Peter?
Yeah, so I'm share your excitement about the coming years, and I think one thing I'm really much looking forward to is when we can have in-person events again, because I find that you learn a lot more by talking to people in a bit more depth than you would in these kind of events. As while this is very interesting, like I think just a more detailed conversation, you can kind of get a better insight into the sort of, from my point of view, the problems, we're trying to enable you to do the real work, and how, understanding what your priorities are helps us do a better job of that. So I think that's my main takeaway.
Tommy, would you close this out?
Sure. Well, I find it exciting, but also terrifying, because I'm looking at the new technologies that are coming, and also looking at our user base and how we're going to support, their needs and requirements moving forward. We, at TACC, we have a very, very diverse application field, and trying to choose the right technology to support, what we need to do for our users and allow them to get their science done. it's really getting to be a bit more challenging. And I mean, it is exciting. I mean, you got all these crazy processors coming, all these types of accelerators potentially available. And we're trying to investigate each one and give them a fair shake. But it's going to be a bit of a challenge over the next 5 years in terms of deciding what's going to be best and work well across the wide range of applications we have to support. So with that, thanks, Keith, and congrats. Our, you know, I'm saying I did hear a rumor that you're about to retire. So wish you well, and hopefully you'll still stay in touch with the HPC community.
I'm hoping I'll pop back up here in the next short period of time. This is still too much fun. Appreciate everybody helping with this and everyone participating. And Michelle, Meredith, thank you very much for organizing this. This was great. Thanks very much.
Hopefully next year we'll be in person.
We will hopefully be in person. And I think between now and then, it will be fun to think about how do we leverage some of the benefits of having a broader community that can't travel. So that'll be a challenge, but we'll give it a go. Thanks, everybody.
Thank you.
Bye.
Thanks.
Thanks.